So, yeah, last time these questions about collisions, they were really annoying because I had to write down equations again and again, and yeah. So what I did was that I just took the head-on collision. I completely analyzed this thing. Yeah, I mean, I made formulae for that basically. So I mean, you have these formulae, so v1 upon v2, but that's only for the special case when your only one of these particles has velocity, right? So initially, but what if it had, yeah, like what if both of the particles had velocity initially? So I made formula for that, and I posted a video about that. Okay, so you can watch that. It's very elementary, and you can do it yourself as well. But yeah, I just had to do it because it was so repetitive. And initially, I thought that okay, maybe like without those formulae, we will be good because right. It's just I mean, two three equations. What could be wrong, right? But no, you have to use a formula for this because this is so lengthy, right? So what are those? First of all, I'll just tell you. I figured out the momentum. So for momentum of I mean any head-on collision, so that will just be so. What momentum are we talking about? We are talking about m2 times v2 minus v1, where v represents the final velocity and u will represent the initial velocity. Okay. So a momentum, which is just m2 times v2 minus v1, that is going to be 2m1 m2 upon m1 plus m2. So something like the harmonic mean, right? But yeah, something like a harmonic mean. And actually it is in fact a harmonic mean. Okay, and that times u1 minus u2, not u2 minus u1, because if u1 is bigger, then you will have a bigger momentum imparted, which makes sense, right? So once you have this momentum figured out, you can just use the fact that this is equal to m2 times v2 minus v1. So basically your, sorry, v2 minus v1. No, not v2 minus v1. It's going to be v2 minus u2, right? Yeah. So v2 minus u2 would be equal to 2m1 upon m1 plus m2 times u1 minus u2. And from here, it's easy. So you can figure out the equations, right? So this is a nice trick to remember. Yes, like this formula, it's so compact and so small, and yet this solves this completely, right? So these things that require two, three equations and a bunch of calculation, now it's so easy to just solve it, right? And what about collisions where you have, I mean, collision at an angle? So I uh, found out that the friction for that kind of collision is going to be zero, and that's why the tangential velocities those do not change, and that means that the tangential kinetic energy also doesn't change, right? So kinetic energy can be split into normal and tangential one. It's doable, okay, right? And from that you can just do okay. Kinetic energy conservation works in only the normal direction, and also momentum conservation works in the normal direction. So these formulas are, I mean, these are still applicable in that for the normal velocities, and for the tangential velocities, I mean, it's a very simple case. Those will be the same as those were before, right? So all of this is just for elastic collision, and I mean, I wish there was something I could do for all kinds of collisions, but no, elastic collision is the best I could do, right? So now we can go to 171 and onward. Okay, a shell flying with velocity something bursts into three identical fragments so that the kinetic energy of the system increases this many times. What velocity can one of the fragments obtain? Oh, shell flying with velocity v is equal to 0, okay, 500 meter per second. Three identical fragments so that the kinetic energy of the system increases identical. That's the main part. Uh-huh. Kinetic energy of the system increases this much times. Okay. What maximum velocity can one of these fragments obtain? You know what I'm thinking? Let's use relative velocities and not this thing, right? I mean, it will work, right? You remember we somewhere before all of this, we derived a formula where we said that the kinetic energy of the whole system is just the kinetic energy as viewed from the center of mass. plus the kinetic energy of the center of mass as viewed in the ground field, right? We could do the same thing because the center of mass is still going with the velocity 500 meter per second, right? That's not changing. And the kinetic energy with respect to center of mass, that is doable because now you can just do like momentum conservation and it will work out, right? Okay, and what maximum velocity can one of these fragments obtain? Ooh, okay, that's a complicated thing because ah, hmm, can one of these fragments obtain? Okay, this is going to be problematic. Well, I mean, these masses are equal, but unfortunately, the momentums are not necessarily, right? So that makes it complicated. Uh, hmm. What do we do? What maximum velocity can one of the fragments obtain? I think I've seen a question. Oh yeah. So this is like neutron. So it's like the I mean, what do we call it? A neutron exploding into a proton and an electron and an antineutrino, right? Something like that. That's what this is, right? Yeah, except that some of those particles were really small and that was much more doable because of that approximation. But over here, it's kind of not doable. Oof. So you know how much the kinetic energy increases. Cool, we can do that, no problem. But oh god, maximum velocity. Ah, the problem is that the velocity is not like just the relative velocity. You also have to account for this thing, right? And that makes it so much not good. Okay, so then what do we do? I mean, of course, we can write equations for this thing, but then it's like three-dimensional or whatnot. Two-dimensional, fine. But still, it's got three momentum vectors, and that doesn't make sense. How can we even solve that? We could limit ourselves to one dimensional, but would this increase the maximum velocity? Actually, yeah, it will. Because the thing is, if you split it into other dimensions as well, those velocities will also contribute to the kinetic energy, right? So in doing so, you are yeah, you are basically decreasing the effect of a single dimension. Yes, because now that is limited to less magnitude of velocities, right? So if somehow you have a solution for this thing, right, where every velocity is not in what do we call it? It's not in a uh, single dimension, right? So what you could do is just delete the other velocities and then whatever kinetic energy those are providing, somehow scale the other velocities so that those provide that much of kinetic energy, right? Because like think about it, maybe your velocities are so in one dimension only are like -1, -2, and 3 or something. And then the kinetic energy provided by this thing is going to be like 1 plus 4 plus 9, whatever. It's like yeah, so 15. And then let's say you want to make this you want to make this go to 30 or something. So what you would do is just multiply each of these velocities with square root 2. So you are just scaling up the whole thing, right? You could do that. So that means any solution with velocities not in one dimension only, that will give us a less magnitude of all of the velocities in some particular dimension, right? So we should neglect all of those solutions and we'll just have it in a single dimension in that case. Perfect. Isn't that right? Okay, this is awesome. Right. And yeah, so let's bring up some equations. So all of these masses are going to be equal, right? So you will just have v1 plus v2 plus v3 is equal to, so that's the m times v1 plus m times v2 all the way, right? That's going to be equal to 3m times whatever this was. So it's just equal to 30. That's what you're saying. Okay. And also its energy increased by whatever like times. Okay. Initially its energy was like half m So let's actually not go with this. Let's say it's going to be 3v. So then this is going to be what? 3v squared or something? No, okay, no. It's just going to be v squared. Sorry, and the mass is going to be 3m. Sorry. So 3m, and then you got v squared right here, and here you just have half m v1 squared, half m v2 squared, so on. So it's like half m v1 squared plus v2 squared plus v3 squared, right? Okay, that's awesome. And then get rid of this thing. So this will be like, okay, v1 squared plus v2 squared plus v3 squared is equal to 3v1. So 3v squared, of course. Oh, sorry. It's supposed to be this times whatever this was, this eta thing, right? So in this case, it's like 1.5. I mean, if it was just v squared, maybe we could use something nice. We could use the RMS thing to get it done. But in this case, no, that's not possible. Okay, so what maximum velocity can one of these fragments obtain? Ooh, that's a bad question. Oh, you could use like Lagrangian multipliers. Is that what they're called? Yes, I think so. So this thing is equal to some kind of constant. This thing is equal to some kind of constant. What we want is one of these to be the maximum. How do we do that? Okay, think. So just say, okay, if you want to maximize v3, you could write this as, okay, 3v minus v1 minus v2. You want to maximize this as a function of v1, v2, right? And under the constraint that, oh, this is not a nice constraint at all. Uh-oh. Oh, wait, okay, what you could do is, so you want to maximize v3, but v3 as it's just like that. It's a function of v1, v2, v3, where the, yeah, like v1, v2 is not here, granted, but it's a function of v3, and we could write it as a function of v1, v2, v3, just with no dependence on v1, v2, right? We could extend it. So, right, let's just say f is equal to v3, so that's our function. These are two constraints. Now I'm going to use Lagrangian multipliers to solve this. Just say like minus 3v equal to 0, and then minus 3v squared, whatever this is, equal to 0. Right. Okay. I don't know how good or bad it's going to be, but we're going to try this. So that will be like fine. So we will define a new function, capital F is equal to f minus, so this constraint, but something times that. So minus alpha times of v1 plus v2 plus v3 minus 3v, and then minus beta times all of this stuff. So like, yeah, summation of vi squared minus 3v squared, whatever this thing is. And we want the partial derivative with this. I know this is little advanced, but I think it's the best way to solve it. And you should really check out that video I made about Lagrangian multipliers. These are like really useful sometimes, of course, not most of the times. But yeah, so we can take a derivative with respect to v1, so partial derivative, and that will tell us, okay, wait, partial f upon partial v1, that's going to be 0. Wow. So for v1, v2, that's going to be 0, but for v3, it's going to be 1. But let's see what happens for v1. So this will just become minus alpha, and then you got minus, let's see. So this is going to be 2v1 and then beta. So 2v1 beta. That should be equal to 0. So you are saying, okay, v1 should be just negative alpha upon 2 beta. Okay, and then v2 should also be the same thing because it's the same thing once again, right? The same process, but v3 not quite the same because this will be like, okay, 1 minus alpha, okay, minus 2 beta v 3 is equal to 0. So that would be like, okay, v3 is 1 minus alpha upon 2 beta, right? So in that way you can maximize the thing. So now I'm just going to put this in here and let's see what we get. One thing we see is that v1 plus v2, sorry, v1 is equal to v2, right? That has to be a necessity. right? So that's one important thing that we got. And you also got all of this. Um, Not sure how this works, but yeah, we could just put these into the constraints and see what we get, right? What alpha beta we get, and if we get something nice, well, it'll work out. Okay, so once again, I'm just writing down the constraints. So you got v1 plus v2 plus v3 is equal to 3 v, right? But then v1 and v2 are just these things, like it's just negative alpha upon beta, and then that plus v2, which is like this thing, so 1 upon, so 1 minus of alpha upon 2 beta, all of that is equal to 3v. Okay, this is helping, I guess it is. Wait, this is going to be once again just a two equation two variable system. No, I'm not gonna do this thing. I'm not going to do this thing because it will just mess up whole, like, yeah, when you will put that right, not gonna do this thing. But one important thing that we did find was that v1 and v2 both must be equal, right? Exactly. So using that fact, and also using that it's only along a single dimension, we can write these constraints differently. So, oh wait, I should not have deleted the whole thing. Just this much will be enough. It's the first time I'm actually using this method anywhere practically. I've never used this Lagrange Lagrange multiplier thing. I only saw it in the derivation for entropy. That's it. That's all I ever used. Yeah, and now you can see it being used in real life. Wow. Okay, let's do it. So v1 and v2 both are the same, so that we can maximize v3. Let's just call them u, and v3 will call as v. So this will be like 2u plus v is equal to 3. Oh, we are already using v. Oh, so then let's not call them that. Let's call them 2u plus v3 is equal to 3v. Ah, I need to name them as something, right? Or what about just a and b? Yeah, you could do that. Take some liberty. So a and b, and then you got this is equal to 3v, and well, okay, what about what our aim is just to find what b should be, right? And then you got another equations that just tells us, okay, cool. It's going to be 2a squared plus b squared is equal to 3 eta v squared, and from here we need to figure out what d is, so we can eliminate, yeah, we can try to eliminate a squared. So taking this, it's going to be 3v minus b, and that guy's squared, right? That's going to be 4a squared, so it's going to be 2 times of this whole thing, so 3 eta v squared minus b squared. Yes, so let's expand this. So you will just have, you know what, for now I'll just say b upon b is equal to x, so that we can deal with this actually easily. So it's going to be 9 minus 6x plus x squared, that's going to be equal to 2 times of eta minus x squared. Yes, so 6, sorry, 3 eta, yeah, so 6 eta minus 2x squared. Yes, now this will be 3x squared minus 6x, and then plus 9 minus 6 eta is equal to 0. So you can get rid of that 3 factor, x squared minus 2x plus 3 minus of 2 eta is equal to 0, right? Wait, what do we want to find? Yeah, what's the maximum velocity? Yeah, right. So we need to figure out what x is. It's not good. Fine. Fine, it's gonna be like x minus 1 squared is equal to 2 eta minus 2 subs. Okay, so x is just equal to 1 plus minus square root of 2 times of eta minus 1. In this particular case, eta is 1.5, so it's gonna be 2 times of 1.5, so it's like plus minus 1. We want to maximize this. We should have the positive quantity anyway, right? Doesn't matter what eta is. So it's just square root of 2 times of eta minus 1. Right. Now once we have x, we can just put that in here and get what v is. So the v3 plus, so yeah, the maximum velocity would just be whatever this was with which whatever it was moving, right? So that velocity, and then that times this x quantity. So it's going to be 1 plus square root of 2 times of eta minus 1. Oh yeah, now we are finally done, huh? And well, if you think about it, we could extend this to more than three particles as well, right? Because that whole method, it wasn't just for three particles. We could have applied this anywhere, right? So if you want to maximize a particular velocity, so a particular particle's velocity, what we could do is just take the partial derivatives with respect to all of the other ones, and that will just tell us that all of the other ones will be equal. And this guy will have some different. Yeah, that makes sense, doesn't it? Perfect. So now that this is done, let's go to, oh, we need to calculate this as well, sorry. So V is 500. And then what is this? 1 plus square root of, so we already calculated this, like 0.5 times 2 is 1, so 1 plus 1. It's going to be 1,000 meter per second. That's so weird. Okay, let's go to 172. Particle 1 moving with velocity something experienced a head-on collision with stationary particle 2 of the same mass. As a result of the collision, the kinetic energy of the system decreased by some whatever. Find the magnitude and direction of the velocity of particle 1 after collision. Ooh. Wait, it's not elastic anymore. Oof. So we'll have to write down the equations again. Okay. Particle 1 moving with velocity something experienced a head-on collision with a stationary particle 2. Same mass. Same mass. Important. As a result of the collision, the kinetic energy of the system decreased by this much. Wait. Isn't this somewhat like previous question? Yeah. It kind of is like, yeah. You know what? You can figure out what the oh wait, this is not slightly different. Fine, but it's pretty much the same thing, right? So all you have to do is momentum conservation, kinetic energy, not conservation, but the equation for that. So both are the same mass. That's an important thing. You can just write V1 plus V2 is equal to V. Okay, cool. Kinetic energy system decreased by this much, so V1 squared plus V2 squared is equal to, it's got 2 times the mass. No, no. No. That's not how it's going to be. Sorry. Particle 1, it just has 1 m of mass, right? And then, yeah, this is the final kinetic energy proportional to the final kinetic energy, and then this is going to be eta times V squared. Yeah, that should do it. So eta times V squared. So that's our equations. Okay, find the magnitude and direction of the velocity of particle 1 after collision. So we want to figure out what V1 is, right? As a silent quantity. It's a head-on collision anyway. Ooh, another quadratic. Let's just say that V1 upon V is X. Well, then that means V2 upon V would be 1 minus X. So this just becomes X squared plus 1 minus X squared is equal to whatever this thing is, eta, right? Yeah, 2x squared minus 2x plus 1 minus eta is equal to 0. And now from it we can figure out what x should be. I guess 172. Magnitude direction of the velocity. Magnitude is kind of hard to do that. Okay, just have to do it. Come on, think about it. Fine, let's do it. Let's actually solve this. You know what, since it's just for a particular case, we could just put this as its value, right? Maybe, but okay, let's not do it because it's gonna be more calculation anyway. So just gonna solve it directly, right? To simplify this, we'll write it like that. Okay, or maybe not. Yeah, let's write it like that. So your x will just be minus b is like 1 plus minus square root of b squared, just 1 minus 4 AC, so it's going to be 2 times all of this. Oh, negative of this. So 2 eta and then minus 2, and all of that upon Oh wait, what? But eta is, oh sorry, it should be decreasing by that. Uh-huh. Oof. Uh, Sorry, it should be like 1 upon eta everywhere. This should also be 1 upon eta. Let's, instead of writing 1 upon, yeah, you know what? Calls the k. So instead of writing eta everywhere, we'll write k. K is just 1 upon eta. So this will be like 2k minus 1. And yes, k is a very big quantity. Okay, and this thing upon 2, that's going to be your x value. And from here, you can figure out what v1 will be. So v1 will just be equal to, and since we just want what? Oh yes, the momentum imparted on this guy is towards the left, I guess, or whatever. That just means v1 should be less than v. So it should be 1 minus square root of all that stuff, right? So it's going to be 1 minus square root of 2k minus 1. It can't be positive. That would make, yeah, that would make no sense. It's got some momentum imparted on it in the opposite direction. How can it be positive? More than 1, that's what I'm saying. Okay. Because clearly 1 plus square root of 2k minus 1 would be a big quantity, really big quantity. So that doesn't make any sense. This is how it should be. 1 minus square root of 2k minus 1 upon 2. Cool. Magnitude wise, it's going to be square root of 2k minus 1 minus 1 upon 2. You get that. You get the idea. Okay, cool. And yeah, k, you have to put that in the, actually, whatever. So not put this as our final answer. So minus square root of 2k minus 1 upon 2, where k, oops, is equal to 1 upon eta. Right. So now calculate. K is, eta was 1%. It's like 1 upon 100. So k will be 100. So it's going to be 200 minus 1, which is like 199. Approximately square root of 200, you could say. Right? Yeah. Yeah. That would make sense. So just got 199 in the square root, 1 minus this guy upon 2. So magnitude wise, so magnitude of v1 is just square root of 199 minus 1 upon 2. Square root 200, I'm not interested in figuring out what that's going to be. Okay. Yeah, this should be enough. And direction opposite to v. Oh, all of this times v, sorry. I almost forgot that. And yeah, like v is just 10 meter per second. So it's supposed to be this times 10. So 10 times this guy. Oof. So like 5 times of all of this. 5 square root of 199. That minus 5. Opposite to v, that should do it. Okay, 173. Particle of mass m having collided with a stationary particle of mass capital M deviated by an angle of pi upon 2, where particle m recoiled at angle 30 degree direction of the initial. So any figure? No, I'll have to draw that out. Stationary particle of mass m deviated by an angle pi upon 2. Okay, right. Okay, fine. Where the particle capital M recoiled at an angle theta equal to 30 degree direction of the initial motion of the particle small m. So small m was going like this. Capital M was in this way. It went up, right? Because it deviated by angle pi upon 2. And this guy just went like that. So 30 degrees. How much in percent? And in what way has the kinetic energy of this system changed after the collision if capital M upon small m is equal to 5? Okay. How much in what percent? as the kinetic energy of the system changed after the collision. Okay, so you just have to do it, I guess. Wait, if it's going by 90 degree, wait a second. Okay, think about it. Uh, it's like this would be the normal surface wherever this is doing. Think about it. We know, like this momentum. So this was stationary, right? So it had no tangential velocity. So only the momentum imparted on it would give you any velocity, right? That means its surface, the surface wherever this interaction happened, it was something like this, perpendicular to this guy. So like making this angle with it. This is 30 degrees, 60 degrees. That's 30 degrees right there. This would have 60 degrees, right? So yeah, it had some tangential velocity, so like 3 whatever. If it had like u, I don't know, this would be u upon 2, and this would be like square root 3 of all that stuff, right? And then the tangential velocity is still there, but this velocity somehow changed, and that's why you have this over here. So yeah, it's doable, I guess. Oh wait, actually you know what this velocity is, so you know what the momentum change is. Wow. Hey, if you know what the momentum change is, I mean, yeah, you can just do it. Oh, it's not, sorry, it's not elastic collision. You cannot apply this formula right away, but still, you know what momentum changes, you can figure out what this guy's velocity will be. And perfect. Okay, so how much has the kinetic energy changed? Right, that's what we want to figure out. Let's go to next page because why not? Okay. This is this guy's velocity, however it might be. You had this surface. It was u in this direction. Now this was 30 degrees, so this must be 60 degrees. Then this angle will be 60 degrees, and that means this is u upon 2, and this thing is square root 3 upon 2 times u. I mean, okay, let's just not use these angles right away. Let's use theta. So this is going to be theta, then this is going to be 90 minus theta, and that would mean that this angle would be theta, right? And you got u over here. So the normal velocity was just u cosine theta, and so this is like u normal, and u tangential was u sine theta, right? And so after this, this starts to, oh yeah, it's pi upon 2 right there. Sorry, I almost forgot that. It's going to be 90 minus theta right there. Yes. So for that, so we know that this is just the tangential velocity. It's going to be u sine theta, and then you got this velocity. So the normal velocity, it's negative, of course. So you can say v normal. That will be negative. And this is like 90 minus theta, so tan of that will be cot theta, just like cosine upon sine. Ooh. So this is going to be u cosine theta right there. Huh. Wait. U cosine theta was the normal velocity. So, huh. Okay, I guess. Yeah, it seems reasonable, you know. It seems reasonable, I guess. But really, if it just went with the same velocity that way, then this would not be 90 degree. Wait, something's just really wrong. No, it's not making sense. I mean, like, okay, this sine theta thing, okay, that's just a tangential velocity as we can see. Cool. And that's normal velocity right there. Like this triangle and this triangle are not same, so these angles are like different. What here you have, oh, oh, it's not 90 minus theta, sorry, this is equal to theta. So this will be like u s squared upon c. Cool, understandable. Right, so v normal is just going to be negative u sine squared theta upon cosine theta, and from here you should be able to figure out momentum. The momentum is, wait, and this was a small m, so small m, and then you got, so initial minus final, that would be the thing actually. Initial minus final, it's going to be mu, and then cosine theta minus all of this. Yeah, it's going to be 1 upon cosine theta. You can just see it right away. Okay, and this should also be equal to whatever velocity this guy gained. Call this thing as v. I don't know, I've already used this, but hey, whatever. So once you know that, you can figure out what velocity this must have gained. Actually, do we even care what velocity this gained? We do. We want to figure out the kinetic energy. We have to care about it. Okay, right. Still kind of weird. It's okay. This didn't change, but this did. Uh, how much in what way? What do we have to write a descriptive answer? I'm not gonna do this. I'm just going to tell you how much it changed. Okay, not in what way. I'm not so fine. Okay, what was I doing? Sorry. Uh, yeah, the kinetic energy change calculation, which is so just this normal tangential, normal kinetic energy, right? Change in that. Oof, so got this guy squared minus this guy squared. That would just be half mu squared, and so this quantity squared is going to be s power 4 upon c squared. Sorry, and that minus of, you know what I'm thinking? No, okay, let's not do that. And that minus of this guy was like cosine squared. So in the end, it's going to be sine power 4 minus cosine squared. It's like sine squared minus cosine squared, if you will. So that's just negative cosine of 2 theta or something upon cosine squared as well. So, it's like sine squared upon cosine squared minus 1. You could say that. Yeah? That makes sense? Well, I guess it does. Yes, it does. Yes, that's right. Okay. So that's sorted. And also the other part, so the other part will just be, oh, you know the momentum. You can figure out the kinetic energy. It's going to be momentum squared half and divided by the mass. So this will just be like this guy squared. So you got m squared u squared upon cosine squared. You will have this 2 and you will also divide by the mass. And there we go. You got this thing. Perfect. So this will be like half mu squared. Let's see, you got s squared upon c squared first minus 1, and then you got this quantity m upon capital M times c squared, and there we go. You figured out how much the kinetic changed. Now, what percentage? Right? So you got to divide this by half mu squared, and there we go. You got the fractional change. Nice, isn't it? Okay, so I'm just gonna put that in there. So tan squared of theta minus 1 plus, okay, all of this, secant squared theta. That should do it. But I'm thinking you could write it completely in secant squared theta, but like, yeah, we could, why not? You could do that. Whatever, just leave it like that. And yeah, that's right. That's all we really care about. Okay, and now let's calculate this thing. So what is theta? It's 30 degrees. So tan squared theta is going to be 1 upon 3. 1 upon 3 minus 1 plus small m upon capital M is going to be 1 upon 5. And then secant squared theta is just, I think it's 4 upon 3. Yes? It's supposed to be 5 right there, sorry. Yeah? So this is like 1 upon 3 plus 4 upon 15 minus 1, which is, okay, 5 upon 15, 9 upon 15 is going to be 3 upon 5, and that minus 1 is going to be minus 2/5. Okay, so it decreased, which is to be expected. I mean, it's not exactly elastic collision. So, yeah, understandable. Right, if it was elastic collision, then angle of incidence would be equal to angle of reflection, right? Because, yeah, approach, no, wait, okay. No, it was slight, I mean, okay, it would be different actually. But we got it, right? We got how it's going to be. Oof. Is this correct? Once again, just check it multiple times. Yes, it must be like that. Okay. is going to be equal to negative 2 upon 5, which, wait, what? Oh, yeah, it's the change in kinetic energy upon the total kinetic energy, which is not what we were looking for. We wanted decrease in kinetic energy upon total kinetic energy. So it would be negative of all of this. But yeah, it's going to be 2 upon 5. Just put mod right there. Actually, no, just put negative, and that will do it. That should be equal to 2.5. Cool. This is done. Let's go to the next question. 174. Oh, okay. So when it meant in what way? It really wanted to say did it decrease or increase? Well, of course, gonna it's just it can only decrease. Okay, it can never increase because these kind of collisions. How would it increase? I don't get that. Okay, but that's how it is. So yeah, that's what we did, right? We just figured out to change kinetic energy, not yeah, that should be the thing. Okay, and it decreased. Okay, this should do it. This should do it. 174. A closed system consists of two particles of masses m1 and m2 which move at right angles to each other with velocities v1 and v2. Okay, right angle to each other. Hmm. I don't. Wait, what? So they didn't even give us a figure. Uh, right. So I think they're saying just v1 and v2 are perpendicular. That's all you're saying. I guess so. Okay, the momentum of each part. So what do they want? Okay, momentum of each particle and the total kinetic energy of the two particles in the reference frame fixed to their center of inertia. Oh, okay. Fine. Understandable. So the center of inertia has, so just use vectors for now. V1 vector, V2 vector is the thing, and then got mass M1, M2. The center of inertia mass, whatever. It will just have M1 V1 vector plus M2 V2 vector, then upon M1 plus M2 and got M1 upon M1 plus M2 over here as well. Right? That would be the thing. That is the velocity of this guy. So relative velocities, that's what you want, right? Or what? Oh, you want the total kinetic energy of the two particles in the reference frame fixed to their center of inertia. And also momentum of each particle. I guess it's not that bad. Fine. So yeah, just figure out what the relative velocity should be. So we'll say relative velocity is u1 and u2. So u1 will be u1 minus all of this. Oh god. Yeah, it's gonna be m1 plus m2. Oh, it's gonna be m2 upon all that stuff, right? So m2 upon m1 plus m2, and that times v1 plus v2. No, this cannot be. But that's oh yeah, it's supposed to be negative. Oh yeah, this guy's gonna have m1 right there, and v1. Okay, this should work out. Yes, it's gonna be negative. And similarly, so like by symmetry, you can say u1 vector will just be equal to m2 upon m1 plus m2. Oh, sorry, u1 m1. Oops. v2 vector minus v1 vector. Okay, so then once we have this, we are looking for the kinetic energy. It's going to be, oh, first of all, we're looking for the momentum, right? So m1 times this guy. So momentum 1 as seen by the center of mass, that will just be equal to m1 m2 upon m1 plus m2 times. Why is this like coming everywhere? I don't know. Sorry. And then you got v1 vector minus v2 vector. So the magnitude of this guy would just be m1 up m1 m2 upon m1 plus m2. This is the square root of v1 square plus v2 square. They want magnitude or what? I'm gonna say They want the vectors, not the magnitude. Cool. So momentum 1 dash, representing that is seen by center of mass. That's going to be equal to m1 m2 upon m1 plus m2 times v1 vector minus v2 vector, and momentum 2 as in a center of mass, that will be what's happening. Okay, that will just be m1 m2 upon m1 plus m2. What is this? v2 vector minus v1 vector. So notice that their addition is going to be 0, which, yeah, I mean, it does make sense, you know. Yeah. Okay, and they want the kinetic energies as well. So the total kinetic energy. So K as in the center of mass. Okay, so this will be like, okay, cool. Um, half mv squared, and we already got what v are. So I think squared. Oh, that doesn't look good. It's going to be really bad. Fine, let's try to do it. So stuff that is common, m1 m2 upon m1 plus m2 squared, that is common. You got v2 squared plus v1 squared, that is common, right? So the magnitude of this guy will just be that square of it, of course. Right. And m2 plus m1, that's what's going to be the other thing, right? Because you will have like half m1 and then this guy squares, okay, half m1 m2 times m2, and yeah, the other stuff. So you got 2 right there. That just means, okay, this cancels away. This is how it is. That's the total kinetic energy. I'm gonna write it in a better format, not write it in a different format. It's gonna rewrite the whole thing. v2 squared plus v1 squared upon 2 times of m1 plus m2. Okay, cool. So this is done. Let's go to 175. A particle of mass something collides elastically with a stationary particle of mass something. Find the maximum angle through which the striking particle may deviate as the result of the collision. Oh, huh. Maximum angle through which the striking particle may deviate. Most likely 90 degrees, but still you can try to do it. So m1 and this is like m2, and the angle between them is like, oh, and these are what, stationary. Yeah, the other guys are stationary. Cool. So it collides elastically with a stationary particle of mass m2. Find the maximum angle through which the striking particle may deviate. Oh, this guy. That makes sense. But and elastic, we can use our formula. Cool. Right. So you got this velocity right here, and then this angle is like theta. Okay. Let's use u. U will be better to use. So you can figure out what this is going to be. This is going to be u cosine theta, which I'll call as un. Yes. Okay, cool. Now let's use our formula. So the momentum will just be 2m1 m2 upon m1 plus m2, and that times of u1 minus u2. Well, u2 is just 0, so it's going to be u. U normal, of course. Which is, okay, let's just face it. It's going to be u cosine theta. Right, this is our momentum. And since we just want the deviation, basically, yeah, like divide this by m1. So there we go. And then do negative of that. So this velocity will be added to this thing, right, in the normal direction. So you got this in the normal direction, and this is like that. It's cool. And we just want the deviation, of course. Ooh. Wait, what? Wait a second. So you got this thing, Also, so like it's gonna be like that. Your tangential velocity changed, your normal velocity didn't change. So maybe like it's here now or something. Yeah. Okay, so your u tangential upon u, sorry. Your u, is this, what is this? Sorry. This is supposed to be u tangential and this is supposed to be u, yeah, like this quantity. It's going to be u normal, right? So your u normal upon u tangential, that is tan of whatever this angle is, right? And then initially it was just 90 minus theta. Now, finally, what will it be? So initial u normal upon u tangential is equal to, that's what we're looking for. Okay, maybe I'm just getting worked upon that thing. Okay, okay, that's equal to pi by 2 minus theta. And then finally, what's going to happen? That's what we are looking for. So let's figure out what the u normal should really be. It's just going to be this, and then you got, so normal guy was just u cosine theta anyway, right? Yeah. So now it's this guy. Well, that should do it. Yeah. Now that's going to be m1 minus m2 upon m1 plus m2 times u cosine theta, right? So now this thing upon the tangential velocity, that will be like u sine theta, right? Yes. This will cancel away. So there we go. M1 minus m2 upon, wait, what? Wait, no. Oh, yeah, actually it is correct. It's tan of whatever this angle is, and initially it was pi by 2 minus theta. So now it's going to be whatever this thing is, like that times cot theta. Cot theta makes sense, actually. It does make sense. So this, oh, sorry, tan inverse of this guy. Yes. Right now, what will happen is that this value will just turn out to tan inverse of this quantity, right? So, I mean, okay, just take reciprocal, that will be like tan inverse of ut minus ut upon 2 un is equal to theta. And then you just take the reciprocal of this guy. So it's going to be m1 plus m2 upon m1 minus m2, and that times tan theta. Does that make sense? I guess it does, because like this angle just became bigger because, yes, as a result of that, it just becomes bigger. And that should do it. Yeah, that should really do it. Yes, that should be the correct thing to do. Of course. There we go. So tan inverse of whatever this is. Okay, and well, that guy and that minus the original theta, that's what we're looking for. Uh-huh. Okay, this is crazy. It's just really crazy. So this is going to be this quantity minus tan theta, and then 1, so that upon 1 plus this quantity times tan theta. Are you serious? That will leave us like nowhere. Oof. Anyway, I'm just gonna write out what that actually is. So it's going to be tan inverse of, so our deflection is just this. Okay, theta. And they told us what theta is, right? No, they didn't. Oh, yeah, it's gonna change with theta. Sorry. Ah, that should do it. Right. This is going to change as theta changes. And we need to figure out, oh, no. Huh. So it was 175. So m1 is bigger than m2 as expected, so that this will be positive and everything. Let's call this thing as a or something. I mean, we could. So we'll just say, okay, it's going to be a tan theta, tan inverse of a tan theta minus tan theta upon 1 plus a tan square theta, right? Which is, okay, a minus 1 tan theta, and then that upon this thing. What? And when will this be the maximum? That's what we're looking for. Are you serious? Ah, well, I mean, you could go to, let's say, 3 times equal to pi upon 2, right? That could be one thing. And then if theta equal to pi upon 2, this whole guy just becomes, it's like a minus 1 times tan theta goes to infinity. Wow. And then 1 upon that upon, oh, yeah, no, it won't work like that. That makes no sense. Ah, but you have to figure out when this will be maximum. Okay, so oh, we could just divide by tan theta. Of course. It should be a tan theta and then plus 1 upon tan theta. And we know by the AMJ inequality that this denominator is bigger than or equal to 2 square root of a. So like this whole quantity will be less than or equal to a minus 1 upon 2 square root of a. That is it. We got the thing. Right. So, and this should happen at, so this should happen when you just have tan square theta is equal to 1 upon a. So, yeah, like theta should be tan inverse of 1 upon square root a. So, theta should be tan inverse of square root of, so like 1 upon m1 minus m2 upon m1 plus m2. That will give us the maximum deflection, right? At this point, you will get the maximum deflection. And what is this maximum deflection? It's going to be a minus 1 upon sort of, so 2 square root of a actually. And this will be what? So this minus 1, it's going to be 2m2 upon m1 plus m1 minus m2 actually. And upon, so 2 square root of this guy's like, oh, that just puts the square root right there. It's going to be 2 square root of m1 plus m2 then. Oh, you could write as 2m2 upon square root of m1 squared minus m2 squared. That will be the deflection. I mean, the tan of that deflection. So tan inverse of this guy is what we're looking for. Yeah. So let's write this out. It's going to be tan inverse of 2m2 upon square root of m2 squared, sorry, m1 squared minus m2 squared. When theta is equal to tan inverse of the square root of m1 minus m2 upon m1 plus m2. That should do it. Yeah. Isn't this just 1 upon a? I guess yes. It's correct. Okay. Yes. This will do it. Fine. So 175 finally done. 176. 3 identical discs ABC, figure 1.45. Ooh, this looks weird. Rest on a smooth horizontal plane. The disc A is set in motion with velocity v, after which it experiences an elastic collision simultaneously with the discs B and C. Distance between the centers of the latter disc. Oh, so elastic collision. Okay, whatever. Smooth horizontal plane. Identical discs. Oh, that's really nice. So hey, by symmetry we could say, okay, these are going with the same velocity or something like that. Okay. So this A is set in this A is set in motion with velocity v, after which it experiences. So v was horizontally. That means yes, symmetry, of course. With disc V and C it collides. Okay, the distance between the centers of the disc between what? Distance between the centers of the latter disc. So B and C prior to the collision. Right. Okay. That is theta times greater than the diameter of each disc. Oh, understandable. Right. Okay. Find the what velocity of the disk A after the collision. At what value of eta will the disk A recoil? Okay, so like in general. This is so unfortunately here are like 3 particles or 3 whatever bodies, and that means our equations are of no use. We could apply it if it was like 2 bodies and it was simultaneous or something. Sorry, if it was consecutive, not simultaneous. but it is not. So now what do we do? I'll have to write all of the equations out. But the good thing is we could just, assume that it was symmetric, even though really this, I mean, there might not even be a need for doing that. But hey, let's do that. Let's assume it's going to be the same. So, okay, let's just say it was U and not V. So if it was U, okay, that's what it came up with. And now it is moving with V, and these two are having momentum P imparted on them. So like now these are moving with velocity. We don't actually even care about what that velocity is, really. Only thing is that you got momentum from here and momentum. Wait, you know what? Okay, what did they give us though? Right, the distance, of course. That's gonna be momentum like that and momentum like that. Ooh, yeah, the thing is, these are elastic collisions, and that's problematic. Ah, fine. Let's just write everything using momentum then, right? And okay, you know what? Let's not use momentum directly, but instead use momentum upon the mass. So if this gains velocity v and this gains velocity v, and then you need to figure out what velocity will this gain. So it originally was moving with u, and now it's gonna gain some other velocity. What will that be? So you use trigonometry for that. This distance between them is what, eta times bigger than the diameter. So then this half of the distance will be like eta upon 2, and yeah, that much bigger than this diameter. So if this was 1, it would be eta upon 2. And yeah, what we are looking for is, so if you got momentum on this disk, so disk B imparted like that, it's gonna be like this on A. We just want its horizontal component. So cosine of whatever this angle is, but this angle is the same thing as that angle, so cosine of that angle is, oh yeah, cosine of that angle is complicated. It's gonna be square root of 1 minus eta squared upon 4. Oof. Oh god. Okay, at least you're making progress. So 2 times of that, it's gonna be square root of 4 minus eta squared. So this times, yeah, that should do it. So square root of 4 minus eta squared like that. That times velocity v. Right? That should do it. So now we can figure out the kinetic energies. Let's do it. So half mv squared plus half mv squared, and what? Just not think about that half. So it's gonna be 2 mv, and also not think about that m. So 2v squared. Okay, plus this guy's energy is going to be like, okay, u minus of v square root of 1. So 4 minus eta squared, all of that squared, and that should be equal to, right, momentum conservation we already did. Now only this will be what we are looking for. This is going to be equal to, so initially it came up with u, it's going to be u squared like that. Makes sense. Okay, let's try to solve this. This will be just really bad. Let's say v upon u is x. So it's like 2 plus, or you could just go with the opposite as well. Nah, v upon u is x. That's better. Wait, what do we look for though? We are looking for, find a velocity of disk A. So we want this quantity. Oh. So then using u as a function of v is better, I guess. Oops. So yeah, just say u upon v is x. Then this whole thing just becomes 2 plus x minus v square root of 4 minus, that v is not here anymore, square root of 4 minus eta squared times, okay, that thing squared. Okay, I get it later. That is equal to 1. No, oh sorry, u squared upon v squared is x. So it's gonna be x squared, right? Just write it down. U upon v is equal to x. Now let's try to solve it. It's gonna be 2 plus x squared plus 4 minus eta squared minus 2x square root of 4 minus eta squared is equal to x squared. So this cancels. You got 6 minus eta squared is equal to 2x square root of all that. Okay, yeah, it's doable like this. So 2x square root of 4 minus eta squared. That should do it. Cool. So now we got x from here. What we are looking for is just this quantity. So yeah, this thing is what we are looking for. Yes. So x will just be equal to 6 minus eta squared upon square root of 4 minus eta squared, right? And that's going to be equal to u upon v. We could just use v as a function of u, I guess. I mean, what did they tell us? Did they give us a velocity? Yes. It's setting the velocity. I mean, I know they gave v. I'm gonna use u, right? That's what I've used throughout this derivation. So velocity v is represented by u over here. What we want to figure out is then this velocity v. Yes. So we'll have to write it like that. V is equal to square root of 4 minus eta squared upon 6 minus eta squared, that times u. Most likely it's correct, but I have a small doubt it might not. Oh, what about this 2? That supposed to be there. Sorry. So 2 times of this guy. That makes sense. Okay, that's there. And what we're looking for is just u minus this v stuff. Okay, it's going to be u squared, and then you got, sorry, not the square, not the square, just looking for this. Yeah, this quantity. This will be equal to u times so 1 minus, and then you got v upon u is just this whole crazy stuff. It's just like 8 minus 2 eta squared, and then upon 6 minus eta squared. Ooh, yeah, that's weird. Okay, so now we can, I guess, do it, and this will be equal to u times, so it's this one negative 2. Okay, and then you got minus eta square plus 2 eta square, it's going to be plus eta square, then upon 6 minus eta square, right? So really it's going to be u times of eta squared minus 2 upon 6 minus eta squared. This is the velocity of A, final velocity of A. Right, so at what values of eta will the disk A recoil after the collision or stop or move? Right, so it will be negative or 0 or positive. You get the idea. Right, let's solve. Oh, and they used V, right? So we also have to use V in the final answer as a vector, of course. Okay, and what do they want? Yeah, conditions. So let's figure out when will this be negative. First of all, yeah, like eta minus, just put this number line thing directly, right? This thing is square root of negative square root of 6, negative square root of 2, square root of 2, square root of 6. So farthest away, eta is like very large. This whole thing will be negative. So like positive right here, negative here, positive here, negative here. I guess that makes sense, right? Okay, and what we want is, first of all, when will it recoil? So for recoiling, what should happen is that eta should belong to, it's weird that it's 3 different ranges, which, yeah, like, why? Huh. Okay, as we save it, so it should belong to, let's see, it goes from negative infinity to negative square root 6. So oops, never include your infinities. Okay, negative infinity, what am I writing? Negative square root of 6 union negative square root 2 to square root 2 union square root 6 to infinity. Oh yeah, that should do it. And when it will stop, so it stops at negative square root 2 and square root 2. So eta belongs to the set negative square root 2 and square root 2, and it will what was the last condition? Move on. when you have theta belonging to, oh, sorry, it should not like that. Oh, and yeah, actually, it should not include square root 6 in any way, and also not these because strictly negative. And square root 6 should not be included in any condition because that just makes this not defined. So wait, what happens like at square root 6? This would be going to infinity. That doesn't make any sense. That seems unnatural. Maybe I made some mistake in doing this. I don't know. Just move on. Move on. What? It's going to be equal to. Oh, once again, never do that. So, negative square root 6. And then negative square root 2, sorry. Union square root 2 to square root of 6. You know what? I'm pretty sure I made some kind of mistake and this is all just wrong. But anyway, let's just continue because I don't want to do it again. So 177, next page. A molecule collides with another stationary molecule of same mass. Demonstrate the angle of divergence. Okay, a molecule with another molecule, it was stationary, same mass, right? Demonstrate that the angle of divergence equals 90 degree when the collision is ideally elastic. Ooh, that's a nice property. Angle of divergence, right? So, wait, what? When the collision is ideally elastic. What do you mean by that? I don't understand this. Wait, what? Differs from 90 degree from, okay, when the collision is inelastic. Not sure I understand this. Why would it be a particular angle? Okay, let's try it out. If this is the surface of the molecule, and then this is the molecule that was going like that. So, right, we had U initially. Now, this is going to impart some momentum on this guy or whatever. Yeah. And then you got some momentum impart on this guy. I mean, why even do that? Just do the formula thing because it's elastic. Aha. So, you got. Wait, what? I mean, if that's the condition, just like think about it. Let's say this is ux and this thing is uy, right? And yeah, but you can figure out the angle of divergence from that. Oh, wait, it can never be equal to 90 degree though. Wait, think about it. You got these two particles, which are not exactly, I mean, surfaces, something like that, whatever. So whenever they come in contact, surfaces like this is what it's doing. This might be moving with some velocity in this direction and some velocity in that direction, right? So it will gain some velocity over here, like this guy will gain that velocity. So now it's gonna go over here, and this guy is going here, yes, and oh yeah. So this will yeah, this will actually work because the thing is like this velocity will completely be transferred to this guy, right? So the formula that we got, momentum is just 2m 1 m2 upon m1 plus m2, and in this case it's just all equal, so it's going to be 2m. So momentum 1 upon m, that will be just 2 and 2 times of u, right? So whatever u it came with, and that little thing. Okay, cool. Right. So once you got that, you can figure out what the velocity of this guy will be. Yeah. I mean, it's just wait, what? Sorry, I think something's wrong. Wait. Okay, something's just really wrong. 2m1 m2 upon m1 plus m2, right? So this upon m, that should give us 2 times of initial velocity stuff. Yes, that is momentum, and initially it was at rest. Now something's not correct about this. Oh, sorry. I understand what went wrong. So M1, M2, and then upon M1 plus M2. That M1 plus M2 gives us a 2 in the denominator. And that's why there's no 2. So it's just going to be U, right? And initially it was stationary. So guess what? Finally, it just has a velocity U. And then kinetic energy conservation and also momentum conservation both mean that this must have zero velocity in that direction, right? Yeah, so it just lost its x component velocity or normal component velocity and just gave this guy that, and it's just moving in tangential direction now. So that's why this angle is 90 degree, which makes sense. So that's what we wanted to prove. So it's just want to demonstrate this thing. Well, it's done. A, done. Or B, differs from 90 degree when the collision is inelastic. Oof. Well, I mean, if it was 90 degree, then maybe we should prove that if it is 90 degree, in that case, um, it just is elastic, right? Nothing else. Ah, that would be so different. Oh, come on, think about it. So you got like friction force acting in this direction, which is doing work. But the thing is, like, it's only increasing the velocities in these directions. The velocities in this normal direction, that is dependent on the normal force. And a normal force by itself, I mean, it cannot do any work. But we know that friction always does negative work. Then how does it increase the velocities in this direction? Because I mean, it's gonna increase the kinetic energy basically. That doesn't make any sense. So I guess it must be stealing energy from velocities in this direction to actually do that. Or it could be like rotating something. Yeah, most likely that's what's going to happen. Yeah, actual molecules have inertia and not just mass, right? They also have inertia, so moment of inertia, and that's why there's just so many factors to account over here. Inelastic collisions will it will be very different, you know. Okay, so B, I cannot just prove it right away, uh, but at least A was a useful thing. Okay, whatever. B, I'm just gonna leave it like that. 178. Because I mean, yeah, like B involves so many different things. It involves rotational motion. It also involves friction and whatnot. Yeah. Okay, just move on. 178. A rocket ejects a steady jet whose velocity is equal to u related to the rocket. Wait, what? Oh, oh, that's weird. The gas discharge rate equals mu kg per second. Why are you putting SI? Demonstrate that the rocket motion equation in this case takes the form this form, where m is the mass of the rocket at a given moment, uh, w is its acceleration, and f is the external force. Okay, okay, that's weird. uh, so what w is the acceleration of the rocket, I guess, and not of the gas discharge. I mean, wait, the gas discharge is going with u, opposite, right, as seen by the rocket, right? Hmm. According to the rocket, it has a pseudo force on it, but then okay, once it leaves the rocket, it's not accelerating anymore. It's just moving in I mean, uniform motion and everything. Whatever. Why do you even care about that? So you wanna apply change in momentum and change in time for this guy. So the force is acting on this is like the external force. That's it. That's all the force is acting on this guy is equal to. So what system are we considering? What I'll say is that consider the gas as well as the ejected gas as well as the rocket as the whole system. Because if you just consider, so yeah, actually I didn't explain this. So that string problem that I stumbled on. sorry, no, the chain problem. There I actually got that out, whether or not F is equal to ma actually, sorry, F is equal to dp upon dt actually works, because it was giving me two contradictory results. But the only thing was that when I was splitting a whole object into two parts, so I was saying, okay, you have this block, you draw an imaginary surface as this block is moving, and figure out what the change momentum of this whole system will be, and yeah, and then figure out the force on this guy, right? And I thought that this force would be equal to the force as I mean on this whole guy, if this was not changing its mass or something. That is absolutely incorrect. Okay, please don't ever do. Yeah, I mean, I fell into this trap. Over here, the force is not just because of the like normal forces that we generally have. Instead, this guy's mass is changing, and that I know the definition wise, the force should be like that, right? That is perfect. Definition wise, force works like that. It's good. But the problem is that over here, um, the the actual forces acting on it. So the force is because of the I mean, I don't know, electrostatic forces and gravity and all that stuff, right? That thing acting on it and the force measured by dp upon dt are different. That is because this guy's mass is changing, right? So there's extra something that is here, and that is because like the mass leaving over here puts a force on this body. It's propulsion basically, something like that, right? Does that even make sense? I guess it should. Right, so it's just good to have actually a well-defined system. Yeah, so we'll define the gas ejected as well as the rocket as a system. And now we want to figure out the dp upon dt for that guy. Yes, right, because internal forces cannot change momentum, so only external forces will. Okay, nothing about it. The rocket is moving up with velocity, whatever. So first of all, figure out the momentum is. So you got all of this gas. So this ejected gas is having some momentum. You got this rocket right here, which is moving up with some velocity v, right? And then it's ejecting gas at a rate of u. Okay, wait, it's ejecting gas at some velocity, relative velocity u, right? So after time dt, what will happen is that okay, this has gone up a bit by. I mean, wait. No, okay, this guy's velocity has changed by v plus dv, right? All of these particles that were ejected before the start of this dt time, those still move with the same momentum, right? So no need to worry about change in momentum of those particles. But the gas ejected, right? You ejected some kind of some gas over here, and yeah, well, it was changing. I get that this guy's velocity was changing, but then let's ignore that. Let's ignore that. So this has um what velocity now? Actually, no. Maybe it's not worth. Maybe we should not ignore that. What do you think? Uh, yeah, no, just ignore that. So in time dt, what will happen is that is like that. Okay, cool. And this guy's mass also changed. So over here it was m. Now it's going to be m minus dm. So dm mass it ejected out with velocity. Oh yeah, so it was dm, and that's why to a first degree approximation it will work even if you don't consider this velocity changing. And this guy's velocity. So relative velocity is u, but upward velocity as seen in the space frame will be v minus u, right? That should make sense, I guess, right? Yeah. So now let's do the dv upon dt thing. So this momentum is going to be m minus dm. Actually, I should say plus dm because we'll just say the mass of the rocket is m. So then this should be negative dm right here. I know, sounds weird, but hey, let's do it. So over here, momentum would be m plus dm times v plus dv, and then minus mv because yeah, right. we got all of these gas particles that were already ejected before this dt1 started. Momentum change of these is not important because that's going to be zero. And then for this guy, the momentum is negative dm times v minus u, right? Yeah, well, that should do it. That's all that's required, really. Yeah, this thing is the momentum in this condition, and this thing is the momentum in the that condition before the time dt, right? Exactly. Yeah, like this whole mass combined is just m, and this is also m. It works. Okay. Now let's see what it's going to be. First of all, you can write this whole thing as dmv, I guess, right? So it's going to be d times mv, sorry, d of mv, which is really just dm times v plus v dm. Yeah. Okay, and then you got this guy. So minus v dm, because yes, plus u dm. So this cancels. You just get v dm plus u dm. Wait, what? Huh? That's unexpected. Okay. It is as it is, really. So you just have v plus u times dm. But all of this actually has to be vectors. So this is v vector, this is v vector plus dv vector, this is all of that, right? But let's forget the vector notation for now. Whatever, just put that in. So v vector plus u vector and then dm. This thing, yeah, and then that upon dt actually. That now this thing is the force, right? So the change in momentum upon change in time of this whole system. This thing will be the force as, yeah. Wait, oh sorry, I messed up once again. Ah, why did I write it like this? So VDM that was already there. This must have been MDB. Sorry. Ah, this is supposed to be MDB. Then all of this is just wrong. So then this upon dt, that would actually give us, okay, mu dm upon dt, which will say, I don't know, like negative this mu. Okay, so negative mu times u. I'm writing in negative mu and then that times u. Both of these are different things, look similar. Plus m times w. So w is dv upon dt, the acceleration. That should be equal to f. And does this become, well, okay, it's different. It's so much different than what I expected it to be. Oh yeah, it should be plus u. What am I doing? Just because it's downward doesn't mean that I have to put a negative sign. It's a vector. Ah, oh, this should be positive there. Okay, so throughout the derivation, this should be positive. Sorry. Oh, come on. Okay, what was I doing once again? It should be negative right here. So then this will be, wait, what? Oh, it should be positive because negative dm upon dt would be mu. That makes sense. So yeah, this is the equation which all in vector notation. Sorry. So f vector minus mu u vector is equal to m w vector. Wow. Hey, that's rocket physics. I know that sounds very arrogant. But seriously, that is like physics for a rocket. What else could we call it? Anyway, so this is the equation that we got. So yeah, nice, done. 179. Oh wait, how did this happen? 179 is a rocket. Oh, so now we have to use this equation. Fine. Moves in absence of external force by ejecting a steady jet with velocity u constant relative to the rocket. That's weird. Why would it be constant? I guess because they want find the velocity v of the rocket at the moment when its mass is equal to m. Forces by ejecting a steady jet with velocity u, okay, constant relative to the rocket. Find the velocity v of the rocket at the moment when its mass is equal to m. If at initial moment it possesses the mass m naught, and its velocity was equal to 0. Make use of the formula given in the foregoing problem. Of course, we're going to do that. Okay, so first of all, plug f equal to 0 in there, and then mu we don't know exactly, do we? No. Actually, yeah, actually we know. The thing is, mu is just negative dm upon dt. Yes, you could use this fact. So now this just becomes, and then u vector should be in the negative as well. Yeah, right. I mean, we could just put it as a vector or something. Yeah, I'm gonna put it as a vector. It's gonna be m dv vector upon dt is equal to negative mu, which is basically just dm upon dt, where m is the mass of the rocket, and that times u vector, right? Of course. So now we have to solve this. Uh-oh. How do I solve this? I cannot divide by vector. That would not be good. Who said to do that? U vector is a constant. That's an important statement. U vector is a constant. Right. This cancels. All you get is just yeah, you got dv vector is equal to dm upon m, and then that times u vector. Why is this giving me natural log stuff? Okay, so integrating, you just get v. What we want is velocity of the rocket at the moment when its mass equal to m. Okay, initial moment it possessed m naught and its velocity was equal to 0. Important, right? So it's going to be v, just v. So v minus 0, I should say, v vector. Yeah. Natural log of, so now its mass is m, and initially its mass was m naught. That times u vector. And if you think about it, m is going to be less than m naught. So this whole thing is just a negative quantity, but then u vector is opposite to what v vector should be, so that negative makes it positive, and it works out, right? So yeah, we got it. We got the velocity. Wow, this formula is so useful. I mean, only when they give us the relative velocity as kind of like a constant thing, but hey, it's useful in this particular condition, so it works. Okay, 180. Find the law according to which the mass of rocket varies with time when the rocket moves with a constant acceleration w. Okay, the external forces are absent, and the gas escapes with a constant velocity u related to the rocket. Oh, so w is constant, u is constant, and its mass at the initial moment equals m naught. This is going to be like, okay, m w vector is equal to, yeah, well, yeah, I'm gonna use vectors because why not, to skip the sign conversions and everything. Okay, so negative mu is just dm upon dt, and that times u vectors. These two are constants, and that's the important thing. So that just means, okay, dt times w vector is equal to dm upon m times u vector. So that means w vector dt is equal to natural log of yeah, sorry, so w vector times t, sorry for that, is equal to natural log of well, it's gonna be m upon m naught. If its initial is gonna be m naught or something. Yeah, that should do it. And then, you know what? Okay, since they didn't give us the things as vectors, it's gonna have to use these as values anyway. So this will now be negative because u vector is actually just negative u. Yeah. So that just means, okay, m upon m naught is equal to e power why? I don't know, wt upon u. So m is equal to m naught e power negative wt upon u. This is crazy. I mean, you are saying a rocket's mass changes like this, an exponential function? I mean, okay, decreasing exponential, but you get the idea. Huh, never thought about it. Okay, nice. Oh, this was 180, I guess, not 179. So this is it. I'll stop for now. See you guys in the next video.